Continuing on from part 4, I've populated another board with brand new parts, and the two modifications we've discussed and checked on the breadboard. One is the output enable bit that you see there. The other one is the direction bit of that bus transceiver, which is now the same signal that goes out to the rest of the system via that pin in the pin header there. That's a masked version of the read-write bit, masked by that NOR chip in there with the halt signal. So in the breadboard this works. Let's see whether it works in the PCB, the little PCB. Let's turn the computer on. And sure enough, it doesn't work. It's the same problem we saw before, which is puzzling. So we have a situation where the same circuit works on the breadboard and doesn't work on a custom-made PCB. So I started looking for things that are different between the two. The first thing I thought was I put large ground planes on 3 layers of the 4-layer PCB, a lot of copper flooding. And I started wondering whether this much metal in the PCB could be having difficulty to establish a common reference with the rest of the motherboard through a single ground pin. Would I get really common ground? And I did a little experiment to see if things would change in a situation where I would add an extra ground wire next to the normal ground pin to the other side of the little daughter board. And indeed, things changed. In one case, we get a cursor. In the other case, we don't get a cursor. This is minor. It's very speculative. I don't think the problem are the ground planes. But anyway, it's one clue. The other thing I've noticed is more than just a clue. I've populated the daughter board with 74 logic using the HCT subfamily. HCT stands for high-speed CMOS TTL compatible, and this is a family of chips used to have a CMOS chip interface with TTL chips in the rest of the board. CMOS chips recognize only very clear values, distinctions between 0 and 1 in voltage. TTL is much more acquiescent of more or less ambiguous signal levels. So we need these HCT chips to make the input signals clear to the CPU, to the CMOS CPU I'm using. The problem is that HCT chips are also relatively slow despite the name. Typical propagation delay would be 18 nanoseconds. Compare that to the 8 nanoseconds that you find in the more traditional LS derivatives of the 74 logic. And sure enough, the clock management and memory management circuitry right above the CPU socket in the motherboard is made of LS chips. So they're much faster than the HCT chips I'm using. The problem is that I use those chips in the daughter board not only to produce signals clear for the CPU, the CMOS CPU on board, but they also produce signals that go to the rest of the motherboard. So I have to be able to interface with both CMOS and TTL as far as levels are concerned and as far as timing is concerned. That's the challenge now. The first thing I did was to replace the two chips responsible for the two-phase clock generation in the little adapter board, replace them with LS equivalents. So I am prioritizing right now timing over signal levels. These little two LS chips will not drive their signal lines very hard, but the timing will be correct. And the reason I am prioritizing timing is that the Atari is a two-clock architecture, very sensitive to timing variations. It's very advantageous because effectively the computer can do something useful not only on the full clock cycle but also on the half clock cycle. That's the advantage of having these two out of phase clock signals. So we have to get the timing right, and that's what I'm doing now. I will worry about signal levels later on. Now, this is the moment of truth. I have put the LS versions of these chips in here so they match the rest of the board. The transceivers shouldn't be time critical. They help have fast signal transitions, but they are not generating any clock or anything. These two guys are clock generation circuitry, so these should be the critical ones. So let's put it in and see what happens. Okay, there we have it. Two non-CMOS chips in here. Let's turn it on and hope for the best. Ha! Yeah, it is testing memory, but obviously the colors are wrong, but it did boot. Now, that's interesting. Let's power cycle it and see if it changes. Yeah, it still has a problem with color, obviously. Power cycle it once again. It is all about timing. It is booting, it just doesn't get the colors right. One more power cycle. Oh, now it did. Eventually it did get the colors right. Huh. Let's power cycle it again. Yeah, during boot, it doesn't get the colors right. I'm not doing anything. Yeah, now it gets. Let's see what happens if I put the cartridge on. Okay, now the cartridge is in place. Still the same non-CMOS chips here. Let's see if the cartridge will boot with the wrong colors. It doesn't, but there is still some blinking. You see? At this point, I decided to just go ahead and design a new version of the PCB for a couple of reasons. One of them, I wanted to eliminate as much as possible the differences between our PCB and the breadboard. So I eliminated the ground plane in the PCB, as you just saw me do. And the reason is the breadboard prototype seems to work much better than the PCB, so I want to reduce the differences between them. And I'm designing the traces, the ground traces, by hand instead of doing copper flooding for them. The other reason I'm going ahead to do this is I want to consolidate the things we've learned so far already. We know that there were some problems in the circuit, and I wanted to put them already in a clean new PCB, a second prototype, to isolate the unknowns and give us the opportunity maybe to tackle the unknowns via some new bodge wires, but not to pile up bodge on top of bodge. I didn't want to do that. Now, as we will see later in this part, it's a very peculiar situation we are facing here, in which the extra parasitics of a breadboard, the extra capacitances, inductances, and resistances that are there while they shouldn't, instead of hampering the proper functioning of the design, which is the case in 99% of the times, in this case, they are serendipitously helping a flawed design appear to work. This is a quite unique situation. Let's see how we are going to deal with it. And with the miracle of video editing, here's the board already received from the manufacturers. There it is, no big ground plane, no copper pouring. Let's just now populate it and see how it works. There's our little adapter board with some non-CMOS LS circuitry for the clock generation part, and two HCT transceivers to provide the CPU with good signal levels. As you see there, it works, it boots fine. To reassure myself that that is indeed the case, I power cycled this thing repeatedly, and it seemed to work well each time. I was surprised. I attributed then the problems we had before perhaps to the large ground planes or just bad luck. And I declared victory a little bit too prematurely. And before I even continued with the restoration, I played games for hours with that little daughter board. And I didn't notice anything wrong with it. And yet there were problems lurking that only became visible if you would pile some stochastic circumstances on top of it, like changes in temperature, humidity, or whatever, the mood of the computer in the day. But at this point, I was pretty satisfied that the electronics part was done, that I had reversed engineered Sally correctly, the computer was stable, and I continued on with the rest of the restoration. Now you guys know that I will be using a transparent case, and I don't like this sticker on top of the lid of the RF modulator. It doesn't look good through the transparent case. I want it to be pure sheer metal. So I'm removing the sticker by boiling it first and then scrubbing the remainings off. And now I proceed to place heat sinks on all the main chips, especially the 5 custom chips, well 4 now since we've replaced Sally. Particularly the Antique and the GTIA get fairly warm, so I wanted to make sure to heat sink them. I'll probably end up heat sinking everything, as you're about to see. I am once again using an anti-static acrylic cleaning fluid to remove the fingerprint I've left on the inside of the case, and also to make sure that there are no electrostatic discharges while I'm installing the board. After the board is installed and standing on the standoffs, it won't touch the acrylic, so electrostatic discharge will not be a problem. But also for aesthetic reasons, I need to make sure to clean up the inside, which I will not have access to later on. Now this case is very beautiful, but one has to be careful with putting the screws on. If you press the screws a little bit too much, the case will crack, and it cracked a little bit for me. Luckily it's a self-limiting crack, but you have to be very careful. Once the screws begin to offer some resistance, you should leave them alone. And voila! Haha, it is done! What a beautiful thing! This is the most unique Atari 800XL in the world today. I challenge you to find another one even remotely like this one. For starters, this one runs without a Sally chip. Beat that! And the adapter fits just right under the keyboard, very snugly. Can you see there? One of the capacitors is almost touching the keyboard, but not quite. It's a perfect fit. I'm very happy with that. The Atari is such a delightful computer architecture. I enjoyed myself playing old childhood favorites like this later version of Space Invaders that you see me play now, and I still have good muscle memory for it. I didn't notice any problems, even when playing Space Harrier that you see me play now there, which pushes the Atari to the limits. The computer seemed to work flawlessly. I didn't notice anything. Only in certain games like this one, if you pay attention to the background image to the left, the colors flicker a little bit in those tree-like things to the left. I didn't even notice it while playing the game, only when I watched the playback that I noticed it. So clearly there is something unstable in the architecture, which I attributed to some faulty joint or bad contacts in sockets, something like that, which I then proceeded to try to fix. But as you will see later, there was something more fundamental than just bad joint or bad contact. So I proceeded to remove all the memory chips and clean their pins carefully and clean their sockets very thoroughly to prevent any bad contact issue, any parasitic resistance or capacitance that was undue. I also changed many of the bad sockets. The Ataris have very bad sockets. I changed them for precision sockets, and in some cases even gold-plated precision sockets. What you see there are the new sockets for the ROMs. The issue certainly has something to do with memory access, so I wanted to cover every base by changing those sockets as well. Even the Antique and the GTIA next to the CPU itself got brand new gold-plated precision sockets. Unfortunately, although all these fine-tuning seems to have helped a little bit, it didn't solve the problems. So let's go back to the schematic and try to figure out where to look for a problem, where to make some measurements. The starting point is this. This is the CPU socket where our adapter is now located. This is supposed to be the Sally chip. We saw that it produces 2 clock signals for the rest of the system in 2 different phases. That's just phase 2 or phi 2, and phase 1 or phi 1, which is in here. Let's follow the paths of these signals to see where we may have some problems. Phi 2 goes up this path in here into an AND gate. The other input of the AND gate is just 5 volts with a pull-up resistor. So this is basically just a buffer. There is nothing really going on in here. And Phi 2 is passed on straight to the Antique, the digital video generation chip, which is this socket there. Now, this is a very simple path. I cannot imagine that there is anything critical in here causing us trouble. So let's go to Phi 1, or the phase 1 clock. It goes into this circuit here. Let me mark out the circuit for you. It's a simple analog circuit. There it is. It produces a signal that is sampled here at this potentiometer. And the sampled signal goes up this path and into the color delay input of the GTIA, which produces the analog video information of the Atari. Now you may think, okay, color delay, we are seeing some color flickering, this may be related to that. It may, but I cannot imagine also that this is a very timing critical circuit. This is just an analog circuit. I can't imagine that some subtle phase difference in the Phi 1 clock is causing trouble here. But Phi 2, let's go back to Phi 2. It goes not only up, it also goes all the way down here through this line, all the way down into this inverter. And what you see here in this square is the memory subsystem of the Atari. These are the DRAMs, the dynamic RAMs, terrible things that require a lot of refresh, a lot of complicated logic. This is the memory management unit, which produces signals like chip select. These are 2 address decoders. They need to be fast in terms of propagation delay, but I don't think there is any problem here either. These chips down here, these are very timing critical. And the reason for that is that if you follow what's going on here, out of this output goes a line all the way up into the RAMs, and this is the RAS signal, the row address select. And the other output of this subsystem also goes up this line here, wraps around there, and that's the CAS input, the column address select of the DRAM. And these are very timing critical signals. The row and the column need to be selected at just the right moment for a read or a write to be done correctly with this RAM. But we already addressed this subsystem here. You see there are a few 74 logic LS chips. This is one of them. That's the LS51. This is just a delay line. I will ignore it for now. And then there are 2 latches in here. That's this chip. That's the LS375. And then there are 2 chips that provide the AND gates. That's a U18 in there. And another chip that provides the inverters. And these inverters are used in several places in this subsystem. These 4 chips are very, very timing critical. They are LS chips, so small propagation delay, but we already addressed this problem by swapping out the clock generation chips on the daughter board for LS equivalents. So this is also already addressed, which it's confusing because, okay, what is left? Well, let me erase this and start clean. We definitely have to go back with the oscilloscope and measure Phi 2 and Phi 1. Just to make sure that the levels are right, that the signal shape looks right. Another thing we can and should do is, remember, this is just the Sally socket in here, but what we are plugging in it is a whole daughter board, a bigger thing, and it has 2 clock generation chips, LS versions now, and combined they produce these clocks that go down there, go up in here, and go up in there, directly or indirectly. There are also two bus transceivers, HCT logic, because they provide the proper level of signals for the CMOS CPU that we have in the daughter card in there. But one thing that sort of escaped my mind is these two chips here, the clock generation chips, not only produce Phi 1 and Phi 2, they also produce the clock for the CPU. Because remember, the clock in the Atari is masked by the halt signal that comes from the antique, namely this signal here. And this is the peculiarity of the Atari. The antique can stop the CPU on its tracks by issuing the halt signal that then masks the clock away. Now, this chip is now an LS chip, no longer an HCT chip, and so is this. This is also LS. So they are compatible with what's happening down here. But now we have an LS TTL chip producing the clock signal for a CMOS CPU. And then the question is this clock signal strong enough? Does it have the right levels for the CMOS CPU? I am not passing this signal through the transceiver. Maybe that's what I should do now to make sure. But first, let's look at this clock signal here. Let's look at its levels, at its shape, to see what's going on. I'm running a game called Laser Gates, because it's the only game where we see the problem with consistency. These bars here are not supposed to flicker like they are flickering. Well, right now not, but this is not supposed to flicker. Some other things in the game are supposed to flicker a lot, but not these two bars and not some of the walls. So this game brings the problem to light. This here is supposed to flicker, but not this is not supposed to flicker, and neither is this. So let's have a look at the clocks while we see the problem on the screen. So this is Phi 1. It's okay, the level is a little low, 3.5 volts. This would not be good enough for a CMOS chip like our W65CO2S. But this is going to the rest of the computer. Yeah, the clock going into the CPU is not it's not what I would like to see. It's under 4 volts. For a TTL circuit, that would be no problem at all. For a CMOS CPU, I don't get any screen. Oh, I do get screen artifacts by touching the clock. If the wall comes, one of the wall... Look, now I am touching the clock. If I release it, you see? Now I'm touching. If I release it, it changes. My oscilloscope probe is at 10x, so it's pretty high impedance. These little circuits here do not have enough signal drive to drive the clock signal hard enough for the CPU. Okay, I've put our little breadboard prototype back to try some modifications to address the problems we just diagnosed. The first order of business is to reproduce the problem we were seeing on the PCB here on the breadboard, and we do reproduce. These are not supposed to blink, and the bars here are not supposed to blink. So this is the clock coming from the motherboard, and it's 4 volts, even a little under 4 volts, so it's pretty weak. But then I am boosting the clock with one of the transceivers, and it will come out on pin 7, 10, 9, 8, 7, and that's much better. It's edging on 5 volts, but that could be a problem as well, because the transceiver is making the rise very sharp, and this changes the timing. So here's what I'm going to do to address these two issues. This network here is the reference clock that comes from the motherboard into the daughter board. And as you can see here, the same network goes into the transceiver, and it's then boosted and is further processed. The problem is that this boosting, as we've just seen, is probably changing the timing of that clock signal, and this is a very timing sensitive architecture. So this is not a good idea. I'm going to remove this from here and I'm going to break this link, I will use these two pins for another purpose. And instead, I'm going to take the reference clock that comes from the motherboard, and I will pass it on untouched, unprocessed, unboosted here to this part of the system. So here we have everything we had before, except that the reference clock is not boosted. It's not going through the transceiver. And now we have freed 2 pins of the transceiver, so we can boost something else. What should we boost? I think it's this. This is the masked clock that is generated by the 7402, which, by the way, they are no longer HCT. These are LS chips now. And the clock generated here goes straight there into the CPU without boosting. And I think that's an error. So what I will do into the CPU, okay, I'll leave it like that. This will be, I'll call it B clock. And then I will boost B clock, making use of that available pin. And the clock of the CPU will come from the boosted version. That's it. So now the reference clock is unprocessed, so the timing is not changed, and then it goes into the two-phase clock generation circuitry, but the clock signal for the CPU that is generated by an LS chip doesn't go straight to a CMOS chip. That wouldn't work. First it goes through the available port in the transceiver, gets boosted, and now it's good for CMOS, and this network here, CLK, it's that one that goes into the CPU. Let's test this in the breadboard. And sure enough, there is no blinking anymore. There is blinking here, but this is what the game is supposed to look like. I know it because I know this game very well. The barriers are not blinking, the energy bars here are not blinking. It's working perfectly. So let's have a look at the signals now. Let's look at the clock signal going into the CPU now. Oh, much better. No changes there. No changes there. It's pretty stable. Nothing on the screen. Of course not, because now it's a boosted buffered signal. It has a lot of oomph now. The transceiver would drive this line very hard, and it rises very sharp, falls very sharply, and the level is almost 5 volts. Yep, the little breadboard prototype is working perfectly. Not one glitch. All signals are looking great. The game does not have a single glitch. We are looking good. Yeah, we are good to make some mods on the little PCB. Okay, so this is the new bodged adapter. There are 3 bodges. One goes from here, wraps around there, and brings the input reference clock to this NOR chip. And 2 pins were lifted in the transceiver, so the masked clock can be boosted through one of the channels in the transceiver, and then it wraps here and goes into the CPU. So now the clock that is boosted is the processed masked clock produced by the two-phase clock generation circuitry here. And the reference clock that comes from the rest of the system, produced by LS logic, doesn't go through the transceiver, otherwise we will lose the timing, as we found out, but it goes straight into the LS logic of the clock generation circuitry of the board. So this should be it. So fingers crossed that this will solve the flickering, and then that will be the end of the project. Okay, 3, 2, 1. So far so good, but we've been here before. So the proof of the pudding is in that game that really flickers laser gates. If this doesn't flicker, then we are done. No flickering! No flickering of these lines here. No flickering of the spaceship. Let's let it run a little bit more. No flickering. Yeah, it is done. It is complete. It is complete. Yeah, no flickering of the barriers. Yeah, this is perfect. No flickering whatsoever. So now, not only does it work, it is flawless. This is it. This is it, folks. And indeed, I have been playing with the computer now for quite a while since I finished it, and it is flawless. There is no flicker, there is no quirky behavior. It behaves exactly like the Sally chip, despite the timing delicacy of the Atari architecture. This has been a very gratifying project. Of course, I'm going to update the project files before I put them up on GitHub or GitHub, whatever you call it. I will update it with the modifications we've made. And then feel free to download the Gerber files, make your own boards, and have fun with this. I will see you next time for the next episode of Pimp My 8. See you, take care. Oh, wait, there is one more thing. At the end of the first stage of Laser Gates, the game we've been using as a reference for the design, you have to kill the boss. And the boss is a 6502 CPU, which you have to blow up to smithereens to pass the stage. Now, what could be more appropriate to end this episode with?